the title says that I'm talking about persistent memory programming in Golang, that's a portion of this talk. I actually took a step back and wanted to describe to you all sort of what work is going on in VMware in the space of persistent memory. Okay. Um, and so, you know, I'll do a very quick introduction of persistent memory as we saw it many years ago when Intel came and actually described it to us, and then describe the current status, some lessons we learned along this journey, because this was actually rather unique for VMware, this journey, in many, many ways. And then, end with a call for action, where VMware can help. The interesting thing for us about persistent memory was that, several of us realized that a large amount of the power consumed in a computer is basically moving data back and forth. In today's programming models, large data structures that are sitting on hard disks get deserialized into random access data structures. That's a lot of data moved, right, from one place to another, and then get operated in RAM and then written back in a serialized form back into hard disks or SSDs, right? And that's more data moved. And just plain old, using persistent memory allows you to use the same data structure in random access format while you're actually computing on it. So the data structure that's used for compute and the data structure that's used for storage is the same. Thereby, you actually save a whole pile of power. And when you are running a data center, these things matter a whole lot. Okay, and we were told at that time that these DIMMs would come at a very high density. And that's actually very useful for us, because when we run large workloads, some of these graphs can run into terabytes, a single graph. If we have to shard it into multiple DIMMs and break down our problem into small pieces, you turn the problem into a distributed systems problem, and nothing in distributed systems is actually easy at all. If we can avoid distributed systems problems, we should. And if we can get scale up to work economically, that's the preferred path. So for us, density is a very, very big play. The sooner the 2 terabyte DIMMs show up, the more happy we will be, right? The fact that the read latency is comparable to RAM is actually very important, because most workloads read more than they write. And the fact that writes are 3 to 5 times slower than DRAM, we can find other ways to kind of cope with that, right? And the fact that you can actually use these things in non-persistent mode, it allows us to go to our customers and say, hey, Intel is producing these DIMMs. Maybe you don't fully trust it. Maybe you don't have your software stack ready to go. But you could just buy these DIMMs, plump it in your machine, and run your software stack with absolutely no modification at all. Get used to the hardware, make your purchase cycle successful, buy the device. And then over time, you can upgrade the hypervisor, upgrade the operating systems, upgrade the guest OS in a gradual manner, right? And that's a dialogue that I think is very, very important to have in a data center scale, especially for VMware, which actually does both private and public clouds, right? So we have to actually talk to hundreds of thousands of enterprises in addition to talking to cloud service providers. Right? And, the interesting thing is I've given this talk a few times, but only now can I actually say the hardware is actually available, right? You can actually go to the Dell website and build yourself a machine today with persistent memory in it, right? Which is not something I could say just even a few months ago. So when we started this program out maybe about 5 years ago, maybe even 6 years ago, we were looking at it and saying, so what do we have to do here? Like, exactly what does VMware care about this? Intel is going to produce this new device, application developers and sort of language runtime owners are going to port. Isn't that enough, right? The truth is the hypervisor needs to change too, because we need to expose a virtualized NV DIMM device into the guest. Otherwise, stuff that you're running inside the guest doesn't see it. Okay, and so we needed to get involved, but then the question is, how deep do we want to get involved? Usually what we do is we just virtualize the device, and then we let the rest of the ecosystem kind of drive ahead in other vectors. But in this case, we actually decided to do more because we felt that we might be standing in front of customers and actually asking them to port to this new device, and they will be sort of looking at us to, do you trust this kind of thing? So we needed to actually get some hands-on experience with this device. So we looked at 3 real use cases. Density, like I said, augment your fast, low-density DRAM with slower, high-density 3D X-point running in non-persistent mode. Large graph processing applications, kind of eliminate the ugliness of scale out. And that's what I meant by a distributed systems problem. And the second class of use cases that we see in our customer base is basically tiered storage. Many of you may have heard about vSAN, which is basically a storage abstraction layer on top of local hard disks. Theoretically, you could see persistent memory appearing as a layer in between. Right? And the third one, which I thought was the one to really be attracted to, is persistence with random access. Using the Loadstore model is not something that the way I look at it, it's one of those revolutions that will happen once every few decades. We moved from 8 bits in address space width to 16 bits pretty fast. We moved from 16 bits to 32 bits, less faster. And then we took a long time to migrate from 32 bits to 64 bits. If I remember correctly, Ubuntu just now retired the 32-bit binaries from its distribution. I think this sort of a change is not going to happen in a long time, where we go from an SSD kind of latency all the way to a RAM-style latency for persistence. That's a 1000x improvement. And no matter what you say, I think true engineering basically makes a lot of things that looked very optimistic seem not so optimistic in the real release. So some of the numbers that I've seen from Intel's chips may not seem great in their first 1.0 product, but I have great faith that every release they'll get better, right? So this is only an up curve that we're sitting on. So for the random access Loadstore use model, we were hoping, this is 4 years ago, that there would be some large vendors like the SAP HANA people who would actually wake up and say, oh, this is good for us too. Let's go and port our application to the Loadstore model. We were hoping other people would do it. Thankfully, I can stand in front of all of you now and say 4 years later that SAP HANA has actually done it. SQL has actually done it. So this is good stuff. And there are people inside VMware who are actually playing around with very large AI models where the neural network gets to be so massive that it doesn't even fit on a DIMM anymore. And they're using higher density DIMMs and Loadstore models for that. So what did we do? First things first, we virtualized persistent memory. What this means is that if your hardware actually has physical NVDIMMs in it, the ESX hypervisor, when it boots on that hardware, will actually allow you to then subsequently build up virtual machines that can have what are called virtual NVDIMMs exposed to the guest operating systems. So if Linux is running inside as a guest operating system, when Linux boots, its tables, ACPI tables will actually tell it that there is a virtual NVDIMM, and it can actually then allow the guest applications to use a Loadstore model. And when it does that, we will actually make sure that the guest load or a store will go straight through to the device and not get intercepted either by the guest operating system or by the hypervisor. Okay, so you will get native performance when you're running your guest applications in the Loadstore model inside the guest. That was a goal. Okay, and in addition, you'll also get all the other cool features, like you could vMotion a virtual machine. You could checkpoint a virtual machine. You can suspend it. You can do scheduling at a cluster level, even though you have persistent memory hanging off of your virtual machines. You'll actually move the persistent memory from one host to another and all that stuff. Okay. And we worked hard to actually make sure that we were ready in our software stack, before the hardware or about the same time that the hardware came out. That was very important for us in this particular project. And this was sort of way we look at inside VMware is that anytime a new hardware feature shows up, we scurry around and try to implement it, virtualize it, whether that's an FPGA, whether that's a GPU, whether that's a new accelerator or anything like that, we scurry around and make sure that that happens. And the reason why that we do that is because we know that there's a reason why these hardware advancements happen. It's because some application is driving that need in the hardware, and we don't want to lose those applications from the virtualization platform. So we'll make sure that the platform is ready. So, what this means is that everything you've heard today, the OpenJDK work, can run inside a virtual machine. Loadstore model. You should not see a performance degradation. If you see a performance degradation, that means we didn't do our jobs well. Okay. And then, we could have gone back and played around with some of these other use cases, the density use case or the tiered storage use case. But, I had 2 people in my team. So and it's a question of what I will deploy those resources for. And I chose the persistence with random access to go off and explore. Right? What I was really looking at, I considered the whole tiered storage as sort of something that will just happen. It didn't look like it had some serious rocket science involved in it. And, I looked at density as also something that will just happen. You could just take a very large application and now run it on this new hardware with a bigger DIMM on it and then kind of analyze this. Didn't seem like there was a lot of unknowns there, so to speak. So we chose the Loadstore model and tried to explore it. And, I was focusing on 3 real questions. See, it wasn't actually clear to me when we started out that this is a net win. We have a situation where the storage stack is like fantastically optimized over multiple decades of work put into it. It's not an easy contender to outrun. And you're now given a device that's, yes, it's faster in hardware than SSD, but the programming model tax is pretty large. You have write amplification for every single write. Now you need to write to a log and to the primary location. And this is happening at the granularity of every store. And it's distributed across the program now. It's not just localized at the fsync or any place like that where you can even profile and say, oh, that fsync is where the problem is. Now it's spread all across the program. It's like an antibiotic that's just gone through your whole body. It doesn't know where the problem is. It just kind of overwhelms every part of your human body, right? Now, how will we debug something like this? It's like a death by 1,000 cuts, right? And so I wasn't very sure whether this write amplification plus the cache pluses would actually overwhelm the performance benefits that I'm getting. And any hardware transition, if you don't have like a 2x or a 3x, it won't get adopted that easily. So I wanted to make sure whether it's not a 20% performance benefit, whereas it's a 2x performance benefit. Right? And the second question was, after you make all those changes to the code base, is it readable? Right? Because the whole notion of programming for persistent memory shouldn't be hitting the person so much in their faces that the programmer is thinking more about persistent memory than about the problem that he's trying to solve. The problem that he's trying to solve should be the primary concern for the programmer. It shouldn't be whether he's calling the right msync at the right place, or is he putting the right sfence at the right place, or is he optimally flushing this or flushing that, or is he cache line aligning the 2 logs? Those kinds of things are just not what you want your programmer, the garden variety programmer, to think about. So the question was, will this actually happen? And we wanted to kind of actually answer it in some quantitative fashion, right? And, you could easily miss identifying a transaction. When you take a 40, 50,000 line program and start porting it to persistent memory, you could miss a transaction somewhere. How do you debug this? How do you know that your program is crash consistent? in real life, right? I mean, and you know, there's an interesting problem here with availability. Persistent memory is a local storage device. Now, if the host catches on fire, we have a problem. We could lose data. In the old world with storage, even though it was slow, it was usually available on the network through some other node. So even if the host catches on fire, you'll get your data, right? So we are going from a world where things were slow, but data was perfectly available, to a place where things are fast, but the data might actually not be available. So we had to make sure that when we go stand in front of a customer and say, you should adopt this new technology, we could have all these ducks in a row. You know? And so I was really basically preparing myself for a conversation that would happen 3-4 years later. Right? So what we did was we decided to modify a real life application. We took an application that we were not familiar with. It was Redis. Nobody in my team knew anything about Redis. It was completely C code, and we knew C. So both my engineers knew C. And I told them, go and understand Redis and modify it. Okay, and I'm going to watch you guys. I'm going to learn from you guys. How much bloody does your hand get? And in the end, do we like what we produce? Is this something that we can live with? We can read it. Can we maintain it? Honestly, can we go to a Redis customer and say, you should be using our fork of Redis as opposed to the Redis Labs Redis? Not that that was ever our intent, right? We never wanted to become a provider of Redis by any imagination. This is just a software engineering experiment. And so we actually wrote a transaction library. And since I wanted to tell an availability story, and I knew Redis actually had different kinds of options where you could run it with 0 data loss, or you could run it with, say, 5 seconds data loss or 5 minutes data loss and so on. But then it would store its data to SSD, which can be networked and accessed across from another node. So it had an availability story sort of built into it. With persistent memory, I built into my transaction library a replication path where when you would log modifications to the persistent memory, it'll automatically batch it and send it off to another node. So that was also hidden from the programmer, so to speak. So he just got replication for free. So we could run our transaction library in 2 modes, either with or without replication. Okay. And so this was the project. Basically, I had 2 people who wrote a transaction library and modified Redis, learned it and modified Redis from scratch. And then, we discussed whether we liked it or not, whether we liked the end product or not. It's a purely software engineering experiment plus a performance experiment. Okay? And during this whole journey, they ran the Redis functional tests, and they also ran the performance tests. Okay? And the entire development of this change that I'm just describing to you happened inside a virtual machine. So just so you know, right? Everything was done inside a ESX virtual machine. So the first thing we did was we virtualized NVDIMMs and checked in that support into our hypervisor. And then we used that hypervisor to port this Redis experiment. And of course, the first thing was, is the performance there? After all this modification, does Redis run any faster? It is, after all, an in-memory database, so it should benefit from this new device. Does it? Right? So this is what it looks like. You have on the bottom row, the bottom thread is the unmodified Redis running on an SSD with 0 data loss. That is, every transaction is actually committed to the SSD. Okay. And the upper row is the modified Redis, hand-modified Redis, done by my engineers. And it also doesn't have any data loss. Okay, so I'm comparing apples to apples from that perspective. Now, you can eyeball it. There is 2x here. Okay, there's even more than 2x at some places. That's comforting. Okay, and this is On the x-axis, you actually have the pipeline depth. So Redis has this notion of a client and a server, and you could have many clients talking to a single server, or you could have one client talking to a server. If you have one client talking to a server, you typically end up noticing just the ingress and egress of the key value latency. You don't actually observe the latency of the data, the hash table on the back of the Redis itself. So in order to actually exercise the backside of the Redis, you need to actually start pumping a lot of data into Redis, which means you either increase the number of clients, or you keep the number of clients the same, but then you make the pipeline width for the server a lot larger so that he just pulls a large number of keys and values in one swoop, and then he processes all of them. And then he comes back and he pulls a large number of keys and values. So he only reads the incoming network packets once, so to speak. And that's what we show on the x-axis. As you increase the pipeline width, we actually perform better than regular SSD. So we actually scale better too. That's an interesting observation that we didn't think that we would get. And the data size that we're using here is 1024 bytes, which is typical for most Redis workloads. I have the same performance results for 32 bytes, 256 bytes, and so on. And in general, we look good. Okay, so the performance is there. Okay, and when I presented this data within VMware, the first response that I got was feedback was that, well, okay, so this is an in-memory database. What's a surprising thing about it? But will a real application actually benefit? And what does a real application mean at that point in time? So we went and scrounged around and asked that question to many of our customers, and they said, oh, well, we have data pipes, we have Kafka data pipes, and these Kafka data pipes will throw some keys and values into a Redis store, and then there'll be some other analytical engine that reads stuff from this Redis store and then kind of prints some stuff out. And of course, I didn't have that application, and none of the customers will actually share the application with us. So I had an intern who actually mocked up that kind of an application. And what he did was exactly that. He basically looked at a Kafka pipe coming from one of our inside data lakes, where there would be Twitter feeds coming through the data pipe. And each Twitter entry will have a geo positioning information. And so what the intern did was he would read those Twitter feeds. He'll pull out the GPS data, and then he will he'll first pump the Twitter feed into the Redis store. And then his analytical engine will read it back from the Redis store, pull out the GPS information, put a pin on a Google map. That's all he did. First year undergrad from UT Austin, that's what he did. So pretty cool stuff. And so what we did was we looked at whether that application actually showed any performance improvement. And so here I'm going to show you something. All right, so on the left and the right, you see two Redises with this whole application that I just described to you. They're both running on the same hardware. The left is unmodified Redis running on SSDs with 0 data loss. On the right, you'll see modified Redis running on PMEM with 0 data loss. And here you'll see number of tweets that were ingested, and then you'll see the speed up, okay, where the X is in the red circle there. Just basically telling you how much faster that the Redis actually get. Right? You can see that there's noticeable improvement. Okay, I mean, this is what we expect our customers to actually see when they buy this device. Plus, they run it inside. All this is running inside a virtual machine also. Okay, nothing is running on physical machines here. So we let it skip for 30 minutes. Now, clearly, the number of tweets that the persistent memory guy has crunched is a lot more than the original guy. We crashed both Redises, and look how fast the persistent memory guy came back alive. You can barely notice that he went down, while the SSD guy is still kind of coming back up. And if you think about what I just showed you here, right, this happens to our customers on a regular basis. Like, for instance, they run Redises that are terabytes in size. They run SAP HANAs that are in terabyte size. The biggest problem is that it's not as if hardware goes down a lot. The problem is when it does go down, which may happen once every 2 years, the warm-up time for the database kills you. You could be warming up the database for hours, especially when you have terabyte-sized databases. You could be warming it up for hours. With this, it's an mmap call, followed by a bunch of page faults, okay, but it's still an mmap call. For the most part, there's not much data copying going on at all. There's no need to warm up anything. Okay, so the service comes up instantaneously. So the example I like to give here oftentimes is, my wife has the property of forgetfully driving the car and then not having enough gas. Okay, so she once even stopped her van in Highway 237, which is a very, very busy highway in the Bay Area, and clogged up the traffic all the way to Palo Alto. Okay. And then I get a call at around 4:30, which is peak traffic time, saying I ran out of gas. Right? So I'm trying to figure out what to do about it. This has happened a few times in different scenarios. And at some point, I basically said, you need to have gas in your trunk all the time. So every weekend, I took it upon myself to make sure that there will be enough gas in her trunk. Right? This is availability. Okay? All right? Human beings have a fantastic way of working around problems that are there around them. If an IT guy has to go provision a SAP HANA database, and you tell him that you might go down for 5 hours every 2 years, maybe, and he's going to say that's just not acceptable because I'll lose my job. And so he's going to buy another machine as an active standby for this first machine, just for covering those 5 hours of downtime that may happen once every 2 years. Let's look at the economics of this for a second. This machine is a 2 terabyte machine. That thing costs like $500,000 easily. You just bought 2 of those. Okay? And you can't even use the second one for running any other virtual machines. He goes to the vCenter scheduler and he basically says, don't do anything on this other machine. Because he's afraid to lose his job. Right? Now, I look at it and say, you know what, if there were gas stations every 10 feet, okay, would I put gas in the trunk of my wife's car? Probably wouldn't. I'd just ask her to walk 10 feet, fill up gas, right? That's the difference here. If Redis could come back up like that, all right, maybe you can save $500,000 of cost for the IT guy. Because it's okay, even if it fails every 2 years, it'll come back up in 3 minutes, 2 minutes, it's okay. It's not the end of the world, right? So I'm really hoping that there's a behavioral change in the IT guy's mind because of this technology, okay? Now, the conclusion here, right, is that the performance improvements are truly real, I think, okay? Everywhere I've looked at, the performance is there, and it's not a small amount of performance. It's 2x, 2.5x, and that sort of stuff. So it's actually something that's respectable. And by the way, we're running this on real hardware. These are Cascade Lake machines with actual CL flush opts on it, which only means that it gets better with CLWBs. Okay? And the reason why CLWB is better than CL flush opt is CLWB does not invalidate the cache line. It just writes it back. So even if there's another hit on the cache line, you will get benefits from it. So it's just purely a benefit as opposed to maybe benefit kind of thing. Now, the second question still remains to be answered. Is the code maintainable? Is this Redis that we modified, hand modified, is it maintainable? Right? And so I just want to sort of show a slide. This is a function that adds a node to a list. And you know Redis is a hash table. It's got a bucket of lists, and this add node function's there. This is just a sample. I mean, I cannot tell you that any one of you can look at this and say, honestly, that this is an add node function. It doesn't look like an add node function. I'm sure all of you have added nodes to a list somewhere in your lives, right? This doesn't look like an add node function to me. So, I mean, clearly, it's just not maintainable. Okay, I mean, you can't take a 40,000 line source code, modify it with all these macros in it, just persistent memory just hits you in your face as an engineer. You hire a new engineer to your software team, he's learning more about persistent memory than about your own software. That's just not the right trade-off to make, right? So at this point in time, I had to conclude the code changes were intrusive. Source code has become really hard to read, which means that, stuff gets fragile as the number of lines of code increases, the amount of bugs you introduce over a certain time period also increases. It's not a pleasant state of affairs. And if you forget a transaction, if you forget a log statement somewhere, engineers can make these mistakes. How do you debug this stuff? It's just a nightmare. And one of the things that my team went through multiple times is that they would just forget to log a particular update to a variable because they did this by hand, remember? Okay, so they would actually go through Redis code, which they didn't understand, and actually introduce logs wherever and all that stuff. They introduce the transactions. If you forget a log, that's a week of debugging, okay? Because you have to crash, and then you won't get the right data back, and you won't know what log you missed, and so it's like picking a needle out of a haystack. So this was not a pleasant state, right? I mean, so the conclusion was, I don't think I would honestly stand in front of a customer and say, you should do this. You should buy this device. You should modify your application. I just didn't think at that point in time I could do that. Okay. And so, we sat around and we talked about this and said, what are the main irritants here? Main irritants are the logging code. It just hits you in your face. The logging code should not be present in the source code. If you can take it out of the source code, life would be much simpler. But how do you take it out of the source code? The restart from crash paths needs to be streamlined. When we did this, we actually introduced the transaction library. We introduced, ability to kind of ask whether this is the first time the program is coming, or is it the recovery, resuming after a crash, and so on. And then if it's resuming from a crash, we'll do different things and things like that. And then we will take care of the possibility of crashing while we're resuming from the crash and things like that. So this is an industrial strength piece of software. It does not, so we actually measured every place that we could fall, we could crash and then recover from that, right? And you could forget transactions, things like that. These were the main irritants, And so we started a second phase of the project, which is really where the talk should start, which is the Golang portion of it. We said, we need to solve these problems too, because we have the performance. We just don't have the software engineering solutions, okay? So our goal was to take an add node function. Now this is written in Go, okay, which kind of looks like an add node function, right? Because it's actually not messing around with persistent memory at all right now. It's just dealing with volatile variables. This is how add node functions should look like, okay? And we wanted to turn this into something like this. Okay, and I told my team that if you can do this, I'm somewhat cautiously willing to stand in front of customers and say, maybe you should do this too, right? And so let's just look at this piece of code, right? There is no log statements here. Okay, there's the transaction start, there's the transaction end, and then we're allocating a persistent memory variable from a heap using a new keyword that Go doesn't actually support today. So there are two keywords here, there's pnew and there's txn. Golang does not support those two keywords today. We've introduced this into our Golang, but this is where we want to go. I feel like this code hides sufficient amount of details about persistent memory into the language itself. Just enough for me to feel like I'm actually programming on my problem, as opposed to kind of taking the bull by the horns and pushing it up the hill and persistent memory thing. Right? I don't want to be fighting that battle. So how do we get here is the question. So we chose Golang because it is 100% open source and a pretty vibrant community around it. So we knew we could ask questions if we ran into trouble. And it's a good systems language, and there's a large footprint of Go inside VMware. A large amount of applications are actually written in Go. And so we split the roles and responsibilities into user, compiler, and runtime. I wanted the user to do what the user knows to do best, because only the user can do, which is identify transactions. Okay, I mean, we can't identify that for him. He needs to tell us where stuff should be consistent. At what point should stuff be consistent? Nobody else can do that. He needs to tell us what variables should go into persistent memory and what variables can afford to stay in volatile memory. We can't do that. Okay. And so let's start with that alone for the user's responsibility. I wanted to change the compiler to take txn and pnew as keywords and automatically generate the logging code. Okay. So the compiler, when it compiles this program, it actually does data flow. It does all the SSA work to figure out that a read of a particular variable is actually a read of a persistent memory instance of that variable. Okay, it figures that out because it does the data flow tracking from the PMU onwards, all the way down. Okay. And it's then able to do automatic log generation, and we have actually programmed it in such a way that you can actually introduce your own logger. So if you have your own fancy logger, which does some flavor of redo log or some flavor of write ahead log that you're used to in your research, you could plug the logger into this compiler and it'll use this logger, the new logger for you. Or if you don't do that, it'll just do a default of undo logging. Okay. And at the end of the TXN, it'll do all the stuff about committing the logs, releasing all the locks that were held during the transaction, and all of that good stuff. So inside the source code, inside the TXN block, you don't actually do any of that stuff. And so same two people, okay, went off now and started learning Golang source code. They were not compiler people, so they learned how to write all of this stuff. And I had two other people also. But Golang community is super proud of their garbage collection and how fast they do their garbage collection. It's truly an amazing language, by the way. The speed with which you build and you run in Golang is just phenomenal. And so we didn't want to hurt that. We didn't want to, just because we allowed persistent memory to objects to sit in a heap, in the Golang heap, we didn't want the Golang garbage collector to suddenly slow down by 20, 30% or something like that. And also we wanted to keep the changes that we make to Golang compiler cleanly separated out so that we can actually have a dialogue with the Golang community and get it checked in step by step by step. Okay? And we wanted to provide a method with which once you allocate an object into the Golang heap, we'll give it a name. And if an object doesn't have a name, it's not reachable, garbage collector will garbage collect that variable. Okay. If it has a name, it's reachable, garbage collector keeps it back. Just as simple as that. So we actually modified the Golang's heap code to accept persistent memory objects. And there's a nuance here that because of all the CL flushes that one needs to do, that all the updates that we do to the garbage collector's internal data structures now needs to be carefully thought through. So we did all of that stuff. And then, we also made changes to the compiler itself to do all the data flow for, log insertion. Right? And, the log is actually an interface, so it actually is pretty powerful. Also, many of the things that I'm talking to you guys about, it's all open source. Any one of you can go and look in the GitHub and actually see what we're doing. It is all work in progress. The compiler work that we have done kind of works. Okay, it is not the best compiler out there. There's lots of places where log statements could be coalesced or other optimizations could be done, and we're not doing any of that stuff. Okay, so there's lots of work and interesting possibilities and opportunities here. Then, how do we take this compiler and compiler that we've written that does all the heap management stuff and say, well, is it good? How do we evaluate that? So we actually wrote the Redis key value store, a fresh instance of it, entirely in Go. Okay, this time so that we could compile that source code with this new compiler that we had built. Right, and by this time we are actually experts at Redis, by the way, right? So we could write this Go version of Redis to mimic the C version of Redis. Okay, and so unfortunately all of this work happened in Redis 3.2. So Redis has progressed. We have not kept up with Redis, but all the Redis benchmarks run on this new Go version of Redis 2. So we could run our functional tests of Redis. We could also run the performance tests of Redis on both the C version of Redis and the Go version of Redis now. And we would do that every night to make sure that things don't regress and so on. So this is purely an engineering project, an engineering project in software engineering and so on. Right? So the question is performance there? The version of Go-Redis that we've implemented is a partial Redis. It's not a full-fledged Redis. Redis is actually a pretty fancy piece of software. It does a lot of different things. We just looked at the key value store aspect of it, the gets and puts. That's all. So the top line The bottom two lines are what you've already seen. It's the same two lines. The top line is a Go version. Okay, right out of the bat, the Go version actually outperforms the C version that we manually inserted, okay, that we manually modified. Now, this is without the compiler even doing a whole pile of optimizations. Okay, I mean, if you actually did the compiler optimizations, it actually should look better. And the source code looks a lot more civilized. Okay, I mean, it looks like Redis code base. It doesn't look like persistent memory code base. Okay, and that's a huge, huge improvement. So you may say, why is the C Redis line worse? It's because we modified it by hand, and we haven't done a great job. We can make it better. We could make it as fast as a Go-Redis one possibly, but we don't care at this point in time. We already have our performance message that we can share with our customer, right? Remember, the goal of this whole effort was to say, can we honestly stand in front of our customers and say, Intel has manufactured this device, hypervisor has virtualized the device, you have many different ways to consume this device. One is as a non-persistent mode, just a expanded memory solution. You also have a way to use it in Loadstore Model. We want you to use it in the Loadstore Model. And if you go down this path, we can help you down that path. That was the whole reason to start this project. And with the second effort with Go, I sort of convinced myself that you can get the performance without introducing fragility into the code base. Okay, but you need language support for it. So let's look at it. We modified Golang, or we're modifying Golang, right? It's not been accepted by the Golang community yet, but we have a fork inside VMware. But a lot of code is written in Java, C++, Rust, Python, R. What are we going to do about all those things, right? And I was very happy to hear this morning that Java has a compiler, OpenJDK that actually does some of the stuff. I think some of our customers would actually be very happy to hear that. I think I would like to motivate someone else to write the Python interpreter, if I can. And, the truth of the matter is my team has a lot of bloody hands in this thing now. We've debugged a large number of crash consistency bugs. We've learned a lot from porting two applications that are in the tens of thousands of lines of code that we don't know, that we were not experts at. And so we've learned a lot from this experience, and we can help others with best practices and so on, and debugging practices and so on, things of that nature. And so I've started having customer conversations cautiously to say, hey, this is a good idea. You guys should move your applications over. And so at this point in time, the work that we have done, I've described. Okay, there's two passes, the C pass and the Golang pass. And sort of what I would like to tell now is like, what did we learn from all of this experience, right? One thing in VMware is that we're very good at doing that first things first, which is virtualize the device. We got that right. After that, there was a question of should we do tiered storage? Should we explore the density dimension of persistent memory? And I'm really glad that we didn't go down those paths, and we took the more challenging Loadstore model question and went down that path. I think we did that right. And virtualizing persistent memory was a good thing to do because I think Intel and VMware worked very closely in that and helped each other along the way. I feel like the Loadstore model exploration has actually kind of produced some good results from the perspective of, can I go talk to a software engineer and say, this is a good thing, don't worry about it, kind of stuff. But what we didn't do right was along the journey, another partner came to us and talked to us about battery-backed DIMMs. And that was a little bit of a distraction for us because of two reasons. First is the battery-backed DIMM is actually a more expensive DIMM. It actually has more hardware in it than a persistent memory module, and it's a more complicated beast. And so it's much more expensive. And I was on the wall about it, and then finally the partner actually stopped building it, which kind of led us down and then pulled us back, kind of thing. So it diluted our efficiency somewhat, and I had a small team. So now what's next? We have a whole pile of Golang code base inside VMware. I'm beginning to do my circuits inside VMware and say, change it, change yourself. We have a Go compiler. It's not the official Golang compiler, but it's our fork inside VMware. And we want to start telling people to start porting their applications while we are working with the Golang community to check in our changes. Okay. And we're also talking with our partners and customers for migrating to this new memory. And there's a whole boatload of backlog of items for improving the compiler and the transaction library. Remember, the two guys whom I actually had working on this thing are not compiler people. So, if compiler people actually pick this up, they'll do a much better job without a doubt in my mind. And there's a lot to explore in the density dimension. That's a dimension that was not explored in this exploration so far. And, I'd like to spend some time thinking about that because to me, a lot of our customers, are forced into the scale out option. They're forced to doing a distributed systems problem because their data sets are huge. And distributed systems is just a nightmare. Just getting it right, getting it maintained, the OpEx of it is just not small at all. I would much prefer to go tell them, hey, there's a 1 terabyte DIMM. It's higher price, pay the CapEx, take the pain, get the DIMM into your system, and then your life is better after that. I think that's a better conversation to have than pay the distributed systems tax, from my perspective. So those are the things that's next. From a summary perspective, it's been a long road. I wish it was smaller. I wish it was shorter. But we've learned a lot. And in the process, VMware has actually built a good deal of expertise, not just in virtualizing the NVDIMM, which we did, but also the software engineering portion of it, so that we can have a more holistic conversation with our customers when we talk to them about this stuff, which is important, I think, because VMware customers do trust VMware a lot, and we don't want to be standing in front of them and saying, go down a path when we don't fully believe it ourselves. Right? So that's really all I had to say. I'll take questions.
One of those languages you mentioned, Rust and Java, have managed runtime.
Yes.
Is there a solution that's possible for C?
Sure. I mean,
C. There's a lot of effort to move it to Go.
So your question is there a solution available for C?
So I imagine that because all of the Redis source was already in C.
But remember, the first pass that we did was entirely in C.
But you said it was ugly.
It is ugly, I understand. So I guess I understand your question now. You're saying that is there a way for the C compiler to do all of this stuff? Right. The answer is yes. It's entirely possible to do. And I kind of omitted it from that list, I guess. That is an unconscious omission. I'll put it back based on your feedback. Yes. I'm sorry, you were first. You've done it for C? Yes. Excellent. Okay. Now, I'm really hoping someone else will do all of this stuff.
I look forward to talk I was going to add. There's some lessons learned from the OpenMT parallelizing C techniques that people have used in for C systems.
Is it also ugly macros?
I mean, some pragma, but it doesn't.
Please. Don't do that. I beg you to actually take a look at the Redis code. It's actually stunningly well-written code. Okay. I mean, it's a pleasure to read that code. But you start putting these macros and pragmas there, it just starts looking unbelievably difficult to debug that. So we really need to think about making it how do you make the right C show up in front of the programmer. Sorry, I didn't mean to cut you off.
Not taking it personally.
Yeah. Okay. I think he was first. Okay.
So I understand why exercises like Redis exercise are done. I've done it several times myself. But I sort of weep inside every time somebody uses persistent memory to make a relational database or a key value store faster. For me, the exciting prospect is making them unnecessary.
Making what unnecessary?
Things like external persistent stores, like relational databases and key value stores. right? If applications manage their own persistence without using a
Oh.
library like Redis,
No,
that's the exciting part.
yeah. And so I'm with you on that one. Like for instance, I remember I said I want to look at the density dimension. One of the applications I'm looking at there is a graph processing application that just goes through a planetary scale social network and does some stuff. There's no Redis, there's no database involved there. It's just a big RAM, this big data structure sitting in RAM. And you're walking the RAM data structure in some random ways. And so that's a completely different exercise. I don't want you to think that all these applications have in-memory databases. I chose in-memory database because that seemed like a ideal candidate to prove a point about persistent memory to the customers, not for any other reason.
I, Terrence's current roommate, would argue that databases are so that applications can be persistent and share their persistence with other applications, not just applications. That's why I use databases.
No, I also didn't interpret his question as no one needs databases. Right? I mean, databases will be around for a good long while. They have a lot of other uses. Right?
You mentioned the frustration of battery-backed DIMMs. Do you include NVDemand in that class?
I'm sorry, could you tell me what NVDemand is? Because I'm
Well,
constantly
NVDemand is a
confused by all this.
flash-backed DIMM that flushes its memory to flash on PowerFill.
Yeah. So let me tell you why I think that way.
Yeah.
My own personal opinion, right? This is not anything more than that. The amount of hardware that goes into one of those DIMMs,
Well, I know.
the electronics,
Firmware in
the electronics that
NVDemand.
goes, yeah, you need to actually have special circuitry to realize the power has gone off first. That has to be synchronized in the system, not just on the DIMM. There's pins out coming from the DIMM to actually recognize that the power is going out. There's a standard for that. There's like a whole pile of work that goes on for that. Right? You see, what happens is oftentimes if you make this mistake of in computer science where for decades we relegate certain pieces of software to be exceptional conditions. The kind of engineers that do that work are not your sort of the same caliber of engineers who actually do other kinds of work. Okay, and all of a sudden we take that and we put it in the front and center. We put it in the critical path. How does the company make that happen? How do you hire the right kind of engineers to actually do that work in a reliable fashion? That's not easy. Just a practical sense, it's not an easy thing to do. So I look at some of these things and it just doesn't fit. And moreover, it's more expensive. It has both NAND and DRAM in it. I don't see why. If you can just wait for a little bit longer and get the right physics to work, I would prefer that. But if the right physics is not there, I would be saying, yeah, go for it.
If it actually works.
Yeah. Yes.
I'll pull up your code example.
Yeah. So I will say that that's not even the most ideal. I would really like it to not even have the p-new.
So in this case, you're adding a node into a persistent list. But if you want a volatile list, then you need, in effect, to have two copies of the code. One
Yes.
for each case.
Yes. So the compiler checks to see if the data that you're operating on is actually a persistent memory object or not dynamically.
And how is it figuring that out?
Because persistent memory is allocated by the runtime in a separate portion of the address space.
This is a compilation of runtime.
Yeah, so the Golang runtime manages the heap objects, right? So you can ask the runtime, hey, is my variable a persistent memory variable or not? And it'll tell you the truth. You can now embed that call into your Go code itself. The compiler could actually generate code that does that check. So, I mean, to be clear, I told you this is work in progress. It's not like all concerns are erased from my head. For instance, the performance of the generated code by our compiler today is not particularly, great. I mean, I could get better performance out of the box from the C-Redis code, but that doesn't mean that's the best it can be. There's just a lot of these kind of checks and so on.
One more question?
So if you don't, I mean, if you don't mind, my request is, we need more bills to actually take some of our other languages. Like Rust is a very popular language. The more language environments that support persistent memory, the more persistent memory is going to get adopted faster. So my request to this team, which is like the group of persistent memory experts in the world, is to go back and try and facilitate something like that happen. I can't imagine VMware going and porting every of these languages, right? That's just not scalable. But it'd be nice if, say, one of you could pick up Python, one of you could pick up R or whatever, and then kind of make it happen. Right? And like I said, when I started this talk, my goal is to make persistent memory actually prominent. I actually believe that it'll actually lower the amount of data moved in a computer system, which is where most of the power is spent. I really like to see that happen. And it's a simpler programming model, if done right. The tools are there. It's actually an easier program to write. And one thing I've not talked at all today is that when you write your program in persistent memory and run it in a virtual machine, there are easier things you can do to debug that code than if you run it on a physical machine. And that's a separate talk in itself. I can go there later on. Thank you.